Most people don't actually grasp what the Big Bang Theory really means, mainly because what's taught in most classrooms isn't entirely correct. I realized this after finishing my physics degree. The version presented to students isn't exactly what many modern physicists believe. When I began writing this video, I intended to explain the Big Bang and prove skeptics wrong. But as I dug deeper, I found that I had misunderstood it myself. Today, the majority of physicists no longer think the Big Bang marked the absolute beginning of everything. What I want to explore is a simple but profound question. What exactly banged? Was it a singularity? Empty space? Nothing at all? Let's unpack this carefully together. And if you can, set aside what you think you know about the Big Bang. You might end up completely rethinking how the universe began. Long before modern science existed, people gazed up at the night sky, trying to explain where everything came from. Ancient cultures filled the heavens with gods and creation stories. The Greek atomists believed space and time stretched infinitely. Meanwhile, Hindus, Stoics, and Buddhists imagined the cosmos cycling endlessly through birth and destruction. Then, in 1687, a 44-year-old Isaac Newton published his Principia Mathematica, revolutionizing how we viewed the universe. He demonstrated that the same physical laws governing motion on Earth applied equally to the heavens. His concept of gravity tied everything together, but it came with a puzzle. If every object attracts every other, why hasn't gravity pulled the entire universe into itself? Newton's answer was inspired by Greek philosophy. He proposed an infinite universe with no center, balanced in every direction so perfectly that nothing would collapse. Thus, our first true model of the cosmos emerged, the static universe. In Newton's view, the universe wasn't only infinite in size, but eternal in time. As a devout Christian, he believed God had created this cosmic structure, yet not necessarily at any specific moment. The static universe became the dominant model, until observers noticed something that didn't fit. When people looked into the night sky, they saw both brilliant stars and vast stretches of darkness. If the universe were truly infinite and eternal, light should come from every direction, making the night sky bright as day. But it wasn't. The darkness meant the cosmos couldn't be infinite and unchanging. Something fundamental had to evolve. 2 centuries later, that change arrived with Albert Einstein. In 1915, he introduced his general theory of relativity, reshaping our understanding of space and time. Einstein showed that as objects move faster, time slows down and lengths contract. At light speed, time would stop entirely. Space and time were no longer separate. They were woven into one fabric, space-time. Gravity, he proposed, wasn't a force between objects, but the warping of this space-time fabric itself. The sun bends space-time, and Earth follows that curve in orbit. Beautiful in theory, but could it be proven? 4 years later, scientists found a way. On May 29, 1919, during a total solar eclipse visible in Brazil, Arthur Eddington led expeditions to test Einstein's theory. If light from distant stars curved around the sun due to gravity, their apparent positions would shift. And that's exactly what the images showed. The starlight bent just as Einstein predicted. Overnight, Einstein became a global celebrity. Headlines proclaimed that Newton's cosmic model had been overthrown. His equations didn't only describe local gravity, they could now describe the entire universe. But his new model faced the same old issue. Gravity should make the universe collapse. To counter this, Einstein introduced a small adjustment, the cosmological constant, representing the energy of empty space. It balanced out gravity to preserve a static universe. Later, Einstein would call it his greatest blunder, though it might not have been a mistake at all. Around this same period, astronomers were turning their telescopes toward the heavens, puzzled by faint glowing clouds they called nebulae, particularly one known as Andromeda. No one knew whether these clouds lay inside our galaxy or far beyond. A brilliant astronomer named Henrietta Swan Leavitt discovered that certain stars, called Cepheid variables, changed brightness in a consistent pattern. The longer their pulse, the brighter they truly were. This discovery allowed astronomers to measure cosmic distances for the first time. Using Leavitt's method, Edwin Hubble examined Andromeda and found that it lay roughly 900,000 light-years away, far outside the Milky Way. Suddenly, the universe became unimaginably larger. What once appeared as cloudy nebulae were actually other galaxies, millions of them. Soon after, another astronomer, Vesto Slipher, noticed that light from most galaxies was redshifted, meaning they were racing away from us at enormous speeds. When Hubble plotted their distances against their velocities, a clear trend appeared. The farther a galaxy, the faster it moved away. The universe was expanding. The static cosmos of Newton and Einstein was dead. Hubble's discovery confirmed predictions made by Alexander Friedmann and Georges Lemaitre, who had already used Einstein's equations to propose an expanding universe. Lemaitre called the starting point the primeval atom, the ancestor of what we now call the Big Bang. Stephen Hawking and Roger Penrose later proved that if the universe is expanding, tracing time backward would lead to a state of infinite density, a singularity, where both space and time would cease. That idea became the standard Big Bang model taught in schools, but it had problems. Reversing the expansion to calculate the universe's age yielded about 1.8 billion years, younger than the Earth itself. Clearly, something was wrong. Even Einstein disliked the concept of a universe with a beginning. He explored models that created new matter continuously, so that density stayed constant, a steady-state universe. But the math never quite worked. Later, other physicists, Fred Hoyle, Thomas Gold, and Hermann Bondi, developed their own steady-state theory, keeping the cosmos eternal. Ironically, Hoyle mockingly called the rival idea the Big Bang during a radio show, and the name stuck. According to the Big Bang idea, the early universe was incredibly hot and dense, a cosmic furnace of subatomic particles. As it expanded, protons and neutrons fused into hydrogen, helium, and traces of lithium. After just minutes, the universe cooled enough for this nuclear process to stop, locking in those exact ratios, about 75% hydrogen and 25% helium. Observations later confirmed this. Roughly 380,000 years later, when the universe cooled to about 2,700 degrees Celsius, atoms formed, and light finally broke free. That first light still travels through space today, stretched into microwaves as the universe expanded. We call it the cosmic microwave background, or CMB, the afterglow of creation. When astronomers accidentally discovered this faint radiation in the 1960s, it became definitive proof of the Big Bang. NASA later mapped the entire sky in this light, using the COBE satellite. Stephen Hawking called the resulting image the greatest discovery of the century. It revealed subtle temperature differences that held the fingerprints of our universe's earliest structure. The CMB also matched the spectrum of a perfect black body, the most precise one ever measured. The Big Bang theory seemed complete, but a few serious problems remained. First, the horizon problem. The CMB's temperature is almost identical in every direction, Yet distant regions of the universe could never have exchanged energy or information fast enough to equalize their temperature. Second, the flatness problem. Space appears astonishingly flat. Any small deviation early on should have magnified over time. Yet somehow, the universe's curvature remains balanced at nearly zero. Third, the monopole problem. Early high-energy physics predicted many heavy magnetic monopoles should have formed after the Big Bang, yet we've never observed even one. And beyond all that, there was still the singularity itself, a point of infinite density that physics simply couldn't describe. It became clear that Einstein's relativity alone couldn't explain the earliest moments. A new idea was needed, one that could reconcile quantum mechanics with cosmic evolution. That idea came from physicist Alan Guth. Guth studied phase transitions, like ice melting or water boiling. He wondered if in the young universe a similar process could have been delayed, supercooled. This delay, he realized, could prevent the formation of magnetic monopoles and drastically affect expansion. In quantum physics, even empty space isn't truly empty. It teems with invisible fields that constantly fluctuate, creating pairs of particles and antiparticles that appear and vanish. This restless vacuum carries energy, and energy, according to Einstein, equals mass. Guth calculated that if the universe were powered by this vacuum energy, it would expand unimaginably fast, exponentially, in a fraction of a second. Space itself would balloon by an incredible factor, flattening any curvature. The universe's geometry would naturally become perfectly flat. He named this rapid expansion cosmic inflation. Inflation didn't just solve the flatness problem, it also explained why distant regions of the CMB share the same temperature. Before inflation, those regions were close enough to equalize, and inflation then stretched them apart. Even the tiny quantum fluctuations within those fields became seeds for structure. Slightly denser spots in the early plasma would later grow into galaxies, clusters, and the vast cosmic web we see today. Without inflation, there would be no galaxies, no us. So, what truly banged? According to this model, it wasn't a singular point exploding, but empty space itself, filled with an inflationary field expanding faster than light. When inflation ended, its stored energy transformed into matter and radiation. That moment, the hot, dense state that followed, is what we now call the Big Bang. And here's the astonishing part. Inflation doesn't end everywhere at once. It keeps occurring in other regions of spacetime, spawning countless bubble universes. Ours may be just one among an infinite multiverse. Still, cosmology keeps evolving. Inflation fits observations beautifully, but it also raises new questions. Some argue it's too flexible or difficult to test. Yet despite its mysteries, it remains our best explanation for how everything began. What we do know for certain is that the early universe was hot and dense. We can literally see its fading glow. That part is not debated. What remains uncertain is what came before that, and why inflation started at all. Alan Guth once said, "The Big Bang Theory never described the bang itself. It doesn't explain what caused it, only what happened after." Modern cosmology continues to explore those unanswered questions, from quantum gravity to multiverse theories. Many people still ask, if the universe began with the Big Bang, what existed before? But that's a misunderstanding of time itself. Time began with space. If space-time had a starting point, then there was no before in any meaningful sense. The singularity model is mostly obsolete now. Inflation provides a better framework, though even it has puzzles left to solve. But that's what makes cosmology so powerful. It's humanity's attempt to understand the origin of everything. We may never have all the answers, but our progress is remarkable. The universe we inhabit is far stranger and more beautiful than anyone once imagined. And now, you understand the Big Bang more deeply than most people on Earth, even many who study physics today. If you found this fascinating, stay curious, because the story of the universe is still being written.